First of all, I'll talk about how to access Spinnaker. And the main way I'll talk about is to access Spinnaker via Jupyter. You can access this via the collaboratory as well, I should say, but you can access the collaboratory basically just accesses this direct URL underneath, which is the spin20.cs.man.ac.uk. And if you do go in via this route, you'll be asked to sign in, of course. If you go in via the collaboratory, you'll instantly be into the system straight away. So you sign in with your eBrain's credentials and off you go. Once you're in, again, if you come in via eBrain's directly, you'll be taken into the Jupyter Lab interface pretty much straight away. But if you come in via this other one, you could have an option of going into the Jupyter Notebook interface as well, which is sort of the older interface. We've just left it there because people have been on the system a while that may prefer to use that. But we'd recommend using the Jupyter Lab interface these days if you're new. When you go in, you get given a window that kind of looks like this. So you've got all these different things. In particular, there's some Spinnaker kernels installed here, and they're the important ones to use. But I'll go into that soon. In this interface, there's a few things that are interesting. There is a work folder. So each person is given a instance here where all your things are stored, and pretty much every time you come in, things wherever you put them will probably be back where you left them. Oh, can I share the link? Yes. Let me just write that in. Yeah, I should explain that I'll do this talk through first anyway, so you don't necessarily have to follow immediately on here. The idea is there's some sort of lab exercises to do at the end, so you can kind of watch this and then do the lab exercise at the end. You're welcome to do things as you go along as well if you want to. But yeah, so everything will kind of be in your notebook space when you leave and come back. It's a bit different from the normal eBrain's Jupyter in that sense, because we're currently separate. We do plan to merge that at some point, and at that point it'll be a bit different. But for now, if you're going to do new things, you're probably best to put them in something like a work folder or the drive folder I'll go into a minute. These are folders that are sort of permanently stored on our system, and it means that if for any reason you want your instance reset, if something's broken or you want to upgrade to the latest install, you can do that and not lose all your work, which is useful. But to be honest, if I was ever going to reset your instance, or one of us was going to reset your instance, we'd ask you to do that first anyway to make sure. There are a few tutorials up here, and one of the things that we'll be doing later is going through these tutorials, so you can have a go at those. There's also the drive folder, as I mentioned before, and that just links you into the eBrain's drive. So it is linked into eBrain's, even though it doesn't use the same lab interface as eBrain's currently. So you can access all the things that you could access in eBrain's in there. If you want to run a Spinnaker simulation, the best thing to do is use this release version here. There's also a Git version here, but I'll talk about that afterwards. When you do that, you'll be given a new notebook and you can start filling in. Of course, I've not done good practice here. I've started it inside the Jupyter instance, not inside one of these shared folders. So, but you can do that as well. That's okay. If you do start Spinnaker and then you're halfway through writing a script and you think, actually, I'd like to try this out in the Git version, or if someone says that that's a good idea, you can change kernel, so you don't worry too much. And that'll just start running it on the other kernel instead. When you are finished with the notebook, it's advised that you close and shut it down. The reason for this is that notebooks kind of have this persistence. And one of the things they do at some point is allocate a Spinnaker board or a Spinnaker machine, a set of boards. And if you haven't ended your script properly, then those boards will still stay allocated and they kind of sit around there allocated pretty much forever. But if you close and shut down your notebooks, that will stop that happening. So it's a good thing to do. It's not an absolute requirement. We'll probably kill things over time if we notice things hanging around that seem to be ancient allocations. But it is nice if you do that, basically. We have installed the autocomplete stuff in Jupyter. So if you are typing along and you think there's something I can't quite remember what it was, you can press the tab key when you're typing and it should pop up with something like this. I've seen it not work on occasion, so hopefully it will pop up with something like this. It just varies, but give that a go. You can also do that with methods. So if you've got your cursor in between the brackets of a method, you're not sure what things you could specify, you can press Shift Tab, and that will give you a little list which gives you the signature of the method or function. So you can see what sort of parameters could be put in there. You can install libraries into the system if you want to. We use this %pip. There is an exclamation mark pip that you may have seen before. This doesn't seem to work. It doesn't seem to pick up the right environment. So if you use the %pip, that does. So you can install anything that you can think of that's useful to you. There are a few things, of course, in there. Obviously, all the things that we use, like NumPy and SciPy, are in there. But if you've got other things that you could find useful or want to link to, you can install them. That's fine. There is a somewhat limited space on the system, but it's quite a large amount of drive space at this point. So we'll tell you if we think you're using up too much. If you want, you can also use the terminal. So you don't have to use just access notebooks. You can actually access terminals, and this gives you something a bit like SSH. There are a few useful things that this can be used for. When you do that, as you can see, yeah, it looks like a normal terminal, an SSH terminal. If you're using the NRP, for example, you might do this. So you can start the NRP by doing CLE nginx and CLE start. If you ever used the NRP before, you'll know these sort of commands, but if you haven't, that's kind of how you kick it off. While we're talking about the NRP, if you then want to access that, you can do so from a URL that looks a bit like this. And I'll put these URLs up later as well, so don't worry too much to access it right now. But basically, you have to put your username in there, and then you get into something like this. There's an NRP user, and I think the password's just password. If it's not password, it's NRP user. I'm pretty sure it's password. Of course, this sounds insecure, but this is your own personal NRP that you've started up. So, of course, you can stop that whenever you want. So people can only access it when you're accessing it, in essence. So, yeah, and they have to know your username, which is so it's a little bit cryptic, but it's not perfect security. But as I say, you can shut that down when you're finished with it. So don't worry too much. There is an NRP storage in here. You can actually see the NRP output here, by the way, as well, once you've done that CLE start. So if you're running things, you can debug things in here a bit. The NRP storage is here, so if you need to edit files and things like that, you can do so from inside the Jupyter system. I've also, other things you can do from the command line I've added is you could update the Git version. So if you're using Spinnaker Git rather than Spinnaker, and you think it might be a bit out of date, I mean, it's fairly the most recent version I just deployed today, so it should be reasonably up to date. But if there's something that you want, or someone's changed something and you want to get this later, or if you're using an older version, in fact, of the notebook, if you've been using an long time user of the system and you didn't get the latest updates today, you can do this manually. And all you do is you change into the folder, you activate the virtual environment, and then you do this git pull, which should update all the different repositories. So that brings everything up to date. Once you have done that, and it's brought everything up to date, you also have to run an automatic make process. This basically goes through and builds all the C code just to make sure that it is in line with everything that's just been updated on the Python code as well. And also there's a bit of Java code in the system as well. This speeds up some of the downloading and uploading of data to Spinnaker. To update that, you also need to rebuild the Java package, otherwise things might get wonky. Once you've done this, you can access that in the Spinnaker Git, as I say. This also had a Spinnaker Jupyter when I was running it earlier. That's just some other environment I've added at some point, but don't worry, you won't see that one. You'll see a Spinnaker Git here. You can start kernels there. As I said before, you can switch into that and then run things on that. But remember, of course, anything that you don't run in the Spinnaker Git kernel won't take advantage of all those things you just did to update. So it's worth thinking about. And finally, when you are finished with the environment, similar to closing notebooks, it's very useful if you log out, simply because it then shuts down the running container. It doesn't delete the container, as I said before. When you re-log in, it restarts your container and you get access to everything you had before, unless you ask for it to be reset. But if you log out, it just sort of frees up the resources that container is using. It'll also make sure any allocated Spinnaker boards do get deallocated at that point as well. So that's an extra double step. Very useful to do. Okay, so I will now talk about the actual spiking neural networks. I'll just cover this just in case anyone's coming here that doesn't necessarily know exactly what they are. It's a very quick introduction to spiking neural networks and what we simulate on Spinnaker. So spiking neural networks, you've got neurons, they have a neuron membrane, and they have a synapse between the neurons. They have axons, things like that. These neurons spike. When they spike, they transfer some amount of charge into the membrane, and the membrane potentially increases, or if you've got inhibitory spikes, it could decrease. When that reaches a threshold, it then fires. And that's kind of what we simulate on the neurons that we have on Spinnaker. The neurons are written in software, so that can be changed, but mainly that's the sort of main detail. We also potentially simulate the synapse movement. So there is a delay that happens when a spike happens. So when a spike occurs, there's sort of a transfer of charge across. There is a delay and also a transfer. So this sort of takes time. So we have synapse shaping, which goes in there. So for example, an exponential synapse shape. So it might be on this side, you're receiving a lot of charge and then slowly decays over time. So we do simulate that as well. So it's worth noting that when you send a spike, it won't necessarily immediately take effect on the other side. And if it's going to cause a spike by just that single input spike, it might take a few time steps before you notice it happening. So Pine, you may have been in the Pine talk earlier, but in case you weren't, I'm going to talk about Pine a bit anyway. But I'll also talk about how it relates to Spinnaker and some of the interesting things, the most useful parts of Pine that we use on Spinnaker networks. So in case you're not sure what Pine is a way of describing neural networks in a way that can run across different simulators. I think the rule is that if any two simulators implement a certain feature, then Pine can also have that feature. And I think there are some other things there. We on Spinnaker use Pine pretty much as is, but we do have some extra things that we also support, which Pine doesn't yet implement because other simulators haven't necessarily implemented it, or we haven't had a discussion on how to make that Pine specific. But yeah, there you go. You can also run things on brain scales. There's a brain scale session, I think, tomorrow. If you want to see that, they'll also be using Pine, I believe. So to use Pine on Spinnaker, you import pine.spinnaker as whatever you like. We often use P or sim. You'll see in quite a few scripts as well. This is an older presentation, so we often just use P for Pine, I suppose. Once you've done that, then you do p.setup, and you can specify a time step if you like. If you don't specify one, you will get 0.1 millisecond time steps. The default Spinnaker run in real-time time step is 1 millisecond time step. So to get that, you have to say time step equals 1. What this means is that simulations will attempt to run in real time when you do this. So the idea is that as simulation goes on, the wall clock goes on, the simulation runs at the same time as the wall clock is ticking. So 30 milliseconds of real time will be 30 seconds of sim time. If you run at 0.1 millisecond time steps, which is the actual default because that's what it is in Pine, the current simulation will automatically slow down by a factor of 10. So it's basically about a factor of what the time step is versus 1. So that means after 30 milliseconds of actual time, it will only have run 3 milliseconds of simulation. Spinnaker does support real time at 0.1 by doing certain extra things, but I won't go into too much detail on those just now. But it is possible to do, just to let you know. What the difference is here, why you might want to change this, is basically if you run in 1 millisecond time steps, it's not that precise. As you see here, you can sort of see the movement of the time. So this is, for example, a membrane plot. If you run at 0.1 milliseconds, it's harder to see that. So it is useful to do in 0.1 milliseconds in certain networks where precision is critical. And that can vary with different neural models, which I'll come into in a minute. How do you describe a population of neurons? You basically say p.population. You say how many neurons are there, and you say what model do you want to run that. You can specify parameters in here as well, change certain things like I offset might specify the some current input that's constant, for example. And then you can give your population a label. You can give it a label of anything you want. I think we restrict you to the unique labels, so I think it will complain if you try and make the same two populations with the same label, but I'm not that sure. It might only be in certain circumstances that's the case. But the idea here is that certain Spinnaker output will use those labels to sort of tell you what's going on. So it can be useful to use reasonable labels for your populations here. Just called this one Fred because it doesn't actually matter. And here's the second population called Bob for no apparent reason. This one has 2 neurons in it. So the populations kind of look like this. They're sort of a blob with lots of neurons in them. And I'll show you some more detail of that later. The various models that we have on Spinnaker, we have more than this, but there's a few obvious ones. We support the most obvious one is the if-currect, which is basically current-based synapses with exponential decay. When I was mentioning the synapse shaping, this is what I was talking about. And these are LIF neurons, so leaky integrated fire. They're about as simple a point neuron as you get. There is also conductance neurons. They tend to require the higher precision to make them work properly. So if you are going to use conductance, I would advise using 0.1 millisecond time steps, but they are there to use. You can run them in real time and see what happens. Izhikevich in the same way, because they're a little bit more of a complex model, it is generally useful to use them at 0.1 milliseconds as well, but that is there as well. In terms of inputs, if you're just wanting to provide some input to your network, you can specify spice source arrays. This is basically just specifying fixed times at which you want spikes to occur. So if there's, here are some spikes, I want them to happen. You can specify the whole population going at the same time, or you can specify different neurons going at different times, so like this. And it's entirely up to you. Similarly, there's a spike source pass-on, has the same sort of thing. You can specify a rate for the whole population for every neuron in the population, or you can specify a rate that is different for each neuron. Entirely up to you. And a pass-on basically just means it's going to be more random with a pass-on generation pattern, which is a common input type in neural networks. Very useful. You can record populations, so you can record what's going to happen when you run your network. The most obvious things to record are V and spike. So V, particularly if you want to see what happened in a network and say, okay, it didn't spike very much, I wonder why. Because the membrane didn't get very high. That's what this looks like. If you plot spikes, if you record spikes, you're basically just recording the time at which spikes occurred for each neuron. So you get a map of neuron to spike. These are graphs, which I'll show you later how to generate as well. You can initialize a population, which basically says, where do you want to set the membrane voltage to? So the initial membrane voltage here is -60. Of course, it changes over time, but that's what it is at the start of the simulation. You can use things like random distributions in there as well. So here's one where I've initialized the membrane voltage to a uniform random distribution from -65 to -55. And you can see here it's sort of randomly started. And that'll obviously affect how the simulation runs, even if they're all exactly the same neuron. That means you get a little bit more random behavior. So you've probably got random spikes here, for example. Once you've got your populations, you then want to connect them together to make a network. And you do that with projections. That is how Pine does it. So we specify a source population and a target population. This is a unidirectional connection now. You can, of course, make a second projection which connects them back to pop 1, but we haven't done here. You specify a connector type, which is what you want the connectivity between the neurons in the population to actually do. And I'll show you a few examples of that in a minute. And we also specify the synapse type. So this is whether it's going to be a static synapse, which basically means it's fixed weight and delay the whole throughout the simulation, or if you want a learning synapse. I'll show you some examples of that later as well. You can also specify whether the synapses are going to be excitatory, which means they're all going to increase the membrane potential, likely anyway, depending on the models, of course. Or you can specify them as inhibitory, which means they tend to decrease the membrane potential and make it less likely that it's going to spike. So some examples of connectors. We have a one-to-one connector. The one-to-one connector does as it says. It connects each neuron in the source to each neuron. It's labeled neuron in the target. So neurons tend to have a number. And so if you target 1 to 1, 2 to 2, if you've got too many in the source or target, that's fine. The one-to-one connector will work out the details and just not connect up those extra neurons. An all-to-all connector connects literally every neuron to every other neuron. So you'll see 1 connects to 1 and 2, 2 connects to 1 and 2, 3, and so on and so forth. Fixed probability connector basically has a probability between each pair of neurons. So here we've got a 10% probability of any two neuron of each neuron pair connecting. So 1 to 1, it says, it rolls the dice and says, does it connect with a 10% probability, and then 2 to 1, and so on and so forth. If you increase the probability, the chances are you increase the amount of connections. Simple as. A fixed total number connector, it's a random choice of which neurons connect, but there's a fixed number of them in total. So here we've got 5 because we've said there's 5. And so that's exactly how many we've ended up with. If we have a bigger number, it will connect more of them, but they are random. It can connect the same pair twice as well. So you can end up with like a multaps. Now, if you're using random weights, for example, you could end up with two different, you could end up adding more weight into that single connection. That is quite useful. And then finally, we also have this from list connector, and this is like a very detailed connectivity. So you're going to say, I'm going to specify exactly which neurons connect to which. So we said 1 to 1, we get 1 to 1. We said 2 to 1, that's what we get. 3 to 2 and 4 to 2, that's exactly the connections that we've made. This connector is very explicit, so it means you get exactly what you want. The downside is it's also very slow to use with Spinnaker. So I warn you immediately, if you're doing anything with a very large from list connector, you may find that your load times on Spinnaker are reduced significantly. Increased significantly. You'll end up with very long load times. So it might make things a lot longer. And that's because we can generate a lot of the connectivity on the machine. We can just send it the description of the connector and then run it on the machine. But that doesn't always happen. So then we have come to the synapse type. So I'll talk about the static synapse first. This connects, as I said before, with a fixed weight and delay. So if we increase the weight, what we're doing is we're increasing the strength of the connection, essentially. So we're going to pass more charge on every spike between the connections. If we increase the delay, we're going to increase the time it takes for the spike to transmit. So this is the limits on Spinnaker. At present are that we can only support up to 144 time steps of delay with the normal models. Now, I mentioned earlier we can support 0.1 millisecond time steps in a different model, and that has slightly different restrictions. But for now, for most of the stuff you're going to do here, it'll limit you to this. And as I say, it's 144 time steps, so it's 14.4 milliseconds if you're at 0.1 milliseconds, of course. And this is 144 milliseconds at 1 millisecond time step. So it varies by time step how much delay you get. You can also specify random weights and delays. So here's a normal distribution of weights, for example, and we just pass that normal distribution in, specifying the appropriate parameters in the weight there. Nice and easy. You can also use a flipped distribution, for example, here. This is quite useful if if you don't want to have massive ranges of weights or delays. You can then clip them because, of course, normal distribution essentially has long tails potentially, so you can stop this happening. Clipped means it basically redraws and puts them into the distribution if they end up outside. The downside of this is if you accidentally specified your distribution poorly, you could end up running this forever. So I think there are some detection mechanisms now that if it tries to do this too many times, it will explode and tell you that it's wrong. But just to let you know. There's also a clip to boundary, which solves that problem because it just puts it on the boundary. But of course, if you poorly specify this, then it means all of the weights that you generate will be the boundary weights instead, which is also not very useful. But that makes sure that you definitely get things in the right range then. We can also deal with spike timing dependent plasticity connections. So instead of static synapses, we can have synapses where the weights can change depending on the activity. And I'll just talk about this a little bit. Say we get a presynaptic neuron spike, and then the post neuron receives that spike. So this is not the post. This is the post population receiving the spike. This is not the actual post neuron receiving it. It's received at the synapse. At some point later on, the post neuron actually sends its own spike, and then actually that spike can travel back down the synapse to sort of the point where the synaptic connection is made. So where there isn't actually, this is before the delays, basically. What we can then do is say there's a gap between the spikes at the synapse. So rather than the spikes as they were sent at the neurons, it's the spikes at the synapse that we're actually accounting for in STDP. We can also do the same thing backwards. The post-neuron might spike first, and then that of course goes down, and then the pre-neuron spikes as well, and that also travels to the synapse. So again, we've got a difference in time that's to do with that gap between the two sides. On Spinnaker, we have a deferred execution model, which means basically the time at which we do the calculation of STDP is on the second spike that you receive. So it's basically on the next spike that you receive from the pre-neuron. So at any spike from the pre-neuron, we do the calculation. One, we do it at this time, the time at which it's sent, because the time at which it's sent is essentially the time it's received on Spinnaker. It's fairly instantaneous, the transmission. So we do it at this time here. And what we do at that time is we look backwards from the spike that we know will be delayed by a certain amount, and we look all backwards from this spike to all the pre-spikes. We then look at the spike that happened before, and we look forward from that to all the post-spikes. So we're basically looking at different times of these neuron things. And the reason I mention this is it can get a bit confusing when you're doing STDP, because you think, I'll just send a single pre-spike and a single post-spike and see what happens. And the answer on Spinnaker is nothing will have happened at that point. There won't have been any calculations done, which means you won't get any STDP effects, which means your weights haven't changed. So if you are going to do an STDP test, a very simple one with single pre and post spike, remember to send a second pre-spike just to make sure that the STDP does get calculated. And at that point, you'll get these calculations like this. And again, it can be a bit confusing, because if you've then had second post spike since, those are not going to be accounted for in this rule. So you've got to be a little bit careful. The way to specify this in Pine is to use the STDP mechanism. So this is what uses your synapse type instead of static synapse. Use this. And you have to specify a timing dependence and a weight dependence, and you specify an initial weight and delay. So you're specifying the initial condition here. You can specify an initial weight of 0, that's fine. And that basically means that initially there won't be any effect of the spike on the post neuron, but the spike will still be transmitted, which means you can still learn something potentially, especially if these two populations have been stimulated elsewhere. You can have that happening. I'll mention a couple of common rules, or one of the common rules in STDP is a spike pair rule. This is basically just looking at all pairs of pre and post spikes and deciding how much the weight changes based on that. So the distance between the spikes is then reflected in this equation here. And what happens is the A plus value that you specified here specifies sort of the difference that's going to happen if they were right on top of each other versus how much it changes over time. So the tau figure here, tau plus, is actually how much this is decaying. So this is basically saying it starts at A plus and over time it's decaying based on the tau plus value. And what we get is a delta A. That's not a delta W, that's not a change in weight yet, because that is used to pass into the weight change rule. Get a little complicated. And I'll just mention, when you do in reverse, it's exactly the same. So it's the difference between the post spike and the pre spike. Now it starts at A minus and it's decaying. And what we get out is a negative alpha value. So this is a negative change, but it's not saying how much the weight is changing yet, because yet again, it depends on the weight rule then. So we now pass that delta A into the weight rule, and one of the common weight rules is an additive weight dependence. This just means that when a certain delta A comes in, the change will be a sort of absolute based on the difference between these two positions. So it doesn't matter if you keep using the same delta A, you'll always get the same change. So the same difference in spike times is resulting in the same change, basically. Obviously, if the spike the spike time difference changes, you will get a different step size. And similarly with a negative one, obviously it's going down by the same as well. And the W max and W min is then all you have to specify here. We also then have a multiplicative weight dependence. This is a little bit more complicated because it changes depending on if you've got a negative or a positive delta A. And what it does is takes account of where the weight is currently with respect to the W max or W min. So the closer you are, the same delta A will make a smaller and smaller change as you approach it. Similarly, if you're very far away, you're going to get a much bigger change. So this is very far away. This was a negative, but it's very far away from W min, so it takes account of that. Whereas these were positive and it was getting closer to W max, so it took account of that difference instead. Okay, so that's a lot of the sort of basics of Pine, and that will let you do quite a lot of our examples. What I will sort of show you now is what happens when you hit the run. So once you've actually described your network, you say p.run and you specify a time in milliseconds that you want it to run, and it is in milliseconds, not time step, so it doesn't matter what time step you set up at the start. This is always going to be in milliseconds. What actually happens then in our software is it starts to break up your network into things that can run on Spinnaker bits. So it's trying to run things on the Spinnaker hardware. It's trying to decide where to put everything. And it might break down your populations into subpopulations, which run on cores like this, for example. What it then has to do is try and route between those. So if it's used multiple chips, so that slide backwards was actually a single chip. Sorry, I'll go back to that. That was a single chip, but you could actually end up placing on multiple chips. Once you've done that, you have to route across the Spinnaker machine. I say our software has to route across the Spinnaker machine and decide where things go to get to their destinations. And it does this using multicast. So it means that things sort of go simultaneously out across the machine. We do have some wraparounds on certain boards, so things can potentially go from one corner back up to the top corner, or across from here to here, or backwards, depending. You can see there are certain points where things go to two places at the same time, so it sort of splits up. Those happen as well. Once we've done that, then we have to, we actually write a lot of parameters down to a database, and that database is then used to load things onto the Spinnaker machine. And this is where I was talking about Java earlier. This is some of what happens with the Java instance. So it loads things from that database onto the machine, which makes things a lot faster. So we've actually run things, and we now want to make a change, and we want to run for a bit longer. So we can actually do that in the Pine language again. What we do is we call set on our population to change some parameter of the population. I wouldn't advise doing this on the synapses, because we currently reload the whole network when you change the synapses. But if you do this on the populations, it actually can reload just that small change that you've done onto the system. So it doesn't take as long then to load. When you're running small networks, generally these things are not that obvious, but when you're running larger networks, these become very useful things to know. So here we've changed I offset, for example, in this population, then we run it for another 50 milliseconds. And at the end, you then probably want to get that data you recorded earlier on. So we can get data, we can choose to get less data than we recorded, that's fine. The software will have extracted all that data that you recorded anyway from the machine. So it's best to only record what you actually want to use later in the simulation, but it won't be an error if you do, say, record lots of things and then only extract one of them. That was fine. So how do we read that data? So the data that comes out is in this NEO format. And again, if you saw the Pine talk earlier, you'll know what this is, I would think, but just in case you haven't, basically it comes in blocks. The block is basically all of the data. There is then a segment. I didn't mention reset, but reset is something you can do in a Pine network. If you do, you basically get a new segment of data. So it starts back from zero again, and starts. But if you've just run one, you will get a segment which you will get a set of segments of which there's a zeroth segment, which you then have to look at. Inside that segment, there are spike trains and analog signals, amongst other things potentially, but these are the main ones that we use. So your spikes will end up in a spike train per neuron. So each of these is a neuron, and it will give you the times that neuron spiked. Each of these is a signal, and it will give you a position value for every time step in the simulation. So here you'll have for neuron 0, you might have, for example, the membrane voltage at every time step in the simulation. So obviously these analog signals are quite large to record, and they do take space on Spinnaker. So you can't run your network for as long, potentially, if you use these, record these analog signals, but you can record them and it will extract them. And our software will work out ways of making it work if you do record them for long simulations as well. So how do you actually do this in code? So you've got your data, you say get data, we've got v and spikes. The V data will be stored here. So data segment 0, analog signals, there it is. The spikes will then be stored in segment 0 spike trains. And as I said, if you haven't called reset, it will always be segment 0. If you call reset, you might also have a segments 1 or multiple if you've called reset a number of times. And we can plot these if we want to. We can use matplotlib as normal. That is also installed in the Jupyter Notebook system. So you create a figure and you plot V times against V naught. So this basically tells the times inside that analog signal. The problem here is we're only plotting one of the voltage values. I'll show you in a minute how you can plot all of the voltage values very easily as well, because Pine has some support for that too. You can do similar thing with the spikes. You can actually plot the spikes directly if you want to. But again, it's quite tricky because you have to sort of form this extra time array and everything, and it gets a little bit complicated. Sorry, this is an ID array for each of the spikes. You probably don't want to do that. To make that easier, Pine actually has its own plotting utility as well. So if you want, you can just pass in the analog signals. You put the star in front of it, which is a special Python thing that says expand this up. So basically we expand each of the analog signals. If you've only got one of them, of course, you'll see exactly the same thing as I showed you before, but you can make a single figure with both these things together, for example. So now we can see the spikes and the voltage occurring sort of at the same time, which is quite nice, quite neat to see. We can also get the weights and delays out of our projection. So if we've run a neural network with STDP, for example, we can see what might have happened to the weights. So this is one example where we have. You can see all the weights are different. We can also do this to see what weights were set when we've used a random weight, for example. We can actually see what values we used. If we use this list format, we actually get basically a source target. Here we've said weight and delay, so we get weight and delay as well. You automatically get the source and target, so you can sort of see which ones are which. You can also use this array format, which you then probably only want to specify one of the things that you actually want, although it will give you an array of arrays and if you don't. This array format gives you one position for every source target pair. So this means you get NaN values, not a number values, where there isn't actually a source target pair. So if this was a fixed probability connector or something like that, there will be places where there aren't any connections, and there we just get this NaN. And otherwise, it's giving you the weights very much as the same as before. So just to tell you, you can go and look at Pine itself and find documentation on this. We support a large number of the things that Pine does now. So if you want to see some extra things, you can have a look at that. There are still a few things we don't support. I don't think we properly support assemblies yet of populations and population views, for example. I think we might support creating them, but I think if you do, you can't create projections between them, essentially. But you can do population views and projections between those if you want to. So you can probably work around that if it really was an issue. And there are a few other things we don't support, but you'll probably come across them quite quickly. If you try them out, it will report errors. Okay, that's the main bit on Pine. I'll now show you some stuff that's kind of a little bit Pine-like, but a bit outside Pine. And this is live input and output that we also support in Spinnaker. Pine doesn't really support this because Pine is designed to support simulators that kind of run and then stop, whereas on Spinnaker you can kind of interact with the system a lot easier. So we can inject spikes into our network literally as it runs, which might be useful if you've got a robot or something you want to send spikes in. And we can do this with a spike injector population. You'll see examples of these in the tutorials later if you want to. Basically what you do is you call send spikes somewhere in the simulation, and this actually fires the spikes at that point. You have something called the Spinnaker Live Spikes connection, which sets up the connection between your simulation and the Spinnaker board. If you've just seen the music presentation, this is something like what's done there. I think when music Spinnaker works, it uses these sort of things directly. So when we call send spikes, it actually sends multicast key into here, which causes a multicast message to be sent over to the various populations that this injector is connected to. So once you've got this, you can just create it. You create it in a population like before, and you can add it into your Pine network. So you create projections from it to other things. You can't project to it, of course, because it's an injector. So you'll get an error if you try to do that. Similarly, if you've got spikes or poissons in your network, you can actually change the rate of those live. So if you set up these poissons, you can add a poisson live rate control to the system, which basically says, I'm going to control these with a live input somewhere. And then you call set rates. This is done with a Spinnaker Poisson control connection, so another complicated long name connection. I forgot to mention in the last slide, but I did mention labels on populations. We actually use the label on population here, so it is critical when you're doing this that you match the labels up with the population, so you do need to give them labels in the first place. When we call set rates here, it again sends multicast keys, so even if your Poisson is split up over the board, it can send the new rates into the various different places on the board to reach your Poisson source and tell it to update the rates at the moment you send the message. We can, of course, also output live spikes. We do an activate live output for, and then we have a receive function somewhere which receives those spikes. We can actually use that same Spinnaker live spikes connection from before, and in fact, you can combine this with the previous one. You just have receive labels here. You had send labels previously, so you can combine those two things together and have a single connection doing all the work. That's fine, no reason why not. This receives multicast spikes from the system and calls this function, which will have your population label in it, time and neuron IDs. So that's going to be a single time with potentially multiple neuron IDs, and you might receive the same time multiple times if there's a lot of spikes. Because basically every time it sends one of these packets, it could send a lot of neuron IDs, and a packet might get full, so it might have to send a few packets to get them. The good thing here is because it's sending your label, you can use the same receive function for lots of different populations if you want to and do different things inside that. But it's up to you. You can use lots of different functions as well. That's okay. And finally, we can also receive live voltage. This is a little bit more complicated. We've kind of designed it around the idea of controlling a robot. So this has a sort of translator interface in the system. And again, you'll see this later if you try it. And we have a special population for doing this, which takes a certain type of model. The idea here is that this lift device model doesn't spike. It just changes voltage. So the population is going up and decaying like a normal lift, but it never reaches a threshold. It doesn't have a threshold to spike with. And this can be useful for controlling motors. So if you use this, basically the idea is it will send you at periodic intervals these packets, which go into this translator, which is called something called translate control packet. So because you're receiving an actual multicast key here, you may want to translate that into something that something external can do, and that's what that's for. So I'll give you just a couple of quick examples as well. So basically, I will let you get loose on the tutorials in a minute if you haven't already started. But I'll show you a couple of extra things that we can also do, and we also have available in the Jupyter environment that you might be interested in. One of these is a breakout simulation. So this is playing the game of breakout, which I've taken an unfortunate screenshot where it's almost finished breaking out all the blocks on this. The idea here is you've got sort of a bat and a ball, and you're meant to bounce the ball to hit the blocks and knock all the blocks, and you're not allowed to let the ball go below this point here, or you sort of lose the ball, and it has to start again. You lose a point, I think, at that point in this particular version of breakout that we've done here. I say you, but actually the idea of this automated breakout that we've got here is that it kind of plays itself, and it makes the bat follow the ball by using a neural network. So if you wanted to go into the environment, you can find this it's actually in the Git environment currently, because it doesn't currently work. Probably works with the release version, but we've set it up so it works well with the Git version. So I thought I'd give you that one. And it's basically under the spin gym. There's a thing called spin gym, and it has examples, breakout, automated. There is a neuromodulated example there. Currently doesn't actually work. It doesn't learn properly how to play the game. Someone is welcome to edit the scripts and things underneath this if they want to and have a go at fixing that. But I'll just mention it there. If you want to try the automated one, you can. The idea is it shows you this game sort of live, and it shows you the spike output from these populations here as well. I also had a request at some point that whether we could run the microcircuit version in here, and the answer is yes. certainly in the latest version, you can run the microcircuit model on here. And we've actually, if you've actually got the latest version, if you haven't logged in before and you get a new Docker, you'll get this. If you have, I can talk you through instructions later on how to update it so you can get this version. The trick is you same thing, you go into Spinnaker Git, you have to activate that environment here. So you have to do this from the terminal. The reason for this is I didn't set up a Jupyter notebook for this so far. You can go into the model, the microcircuit model, and just run it. Simply as that. It does take about, I think, 10-15 minutes or so to actually run through the whole example. When it has finished, you may get outputs that look a bit like this, which might make you worry and think things aren't working. Basically, it says some packets arrived that are too late to be processed in the given time step. The reason for this is it's running in real time. And sometimes, yes, it doesn't quite manage to keep up with all the packets flying around. However, the microcircuit is a reasonably resilient model, and losing a few packets is actually okay. So losing these 1,000 packets over the entire simulation run, which is about, I think it's 1 second run, isn't that critical. There's plenty more packets that are controlling this. If you lose a lot more than that, it does tend to start to explode and you'll see issues. But if you're losing these sort of numbers, it should be fine. There's also then a results. Sorry, I should have shown you that in the last slide. There is a results folder here then. You can't see the full path here, but it is in the Spinnaker Git microcircuit model results. This is actually, when it's finished running, you can actually see a PNG of the activity. And this should be what it looks like, which is a sort of familiar, if you've ever seen these runs, they're quite familiar in terms of the rates, sort of going up to just over 8 Hertz in this particular model, and then sort of coming down and up again. That's quite a common run. So if you run that, you should hopefully see those results if you want to have a go, something like that. For anyone who's not ever tried anything on Spinnaker, you may want to try these tutorials, or even if you have tried things on Spinnaker and you're interested in making sure that you're up to date with things, you can try these tutorials, which are on the spin20csman.ac.uk. That should be in the chat, but I'll put it in a second time because I'm aware that some people have joined and left and so on. So to make sure it's there, I'll put it up again. If you go into there, you should be able to log in with eBrain's usernames and passwords, and then you should be able to see folders on the left which have these running Pine simulations and live input and output. Now, if I can get my version up, it's not actually kicked off mine yet. I'll have to go into mine now. I'm hoping you can see my screen still. Yeah, this is what it looks like inside. So you basically see this 01 running Pine simulation. You go in there, there's actually a notebook within that called Running Pine Simulations on Spinnaker.ipynb. If you open that, it's kind of similar to the presentation I just gave. It kind of goes through a few of that detail. So if you want to skip a lot of that, that's fine. If you want to read through it again to make sure you've got it. At the end, there are then some exercises that you can have a go at. So for example, you can click on here and it'll open up a new notebook. The idea of the notebooks that it's got here is that they have sort of fill in the blank. So you can sort of say, okay, it tells you what to do. You have to try and work out what to put in the space, and then you can sort of run all the different bits. It's got a couple of extensions at the end if you want to as well. You can try those out in a sort of extra blank space. If you don't want to cheat by having the fill in the blank, for example, you can actually just read the description as well. Although that will be a harder way of doing it, of course, which just says create a network and try and see if it runs. The extensions are still in the notebook, I'm afraid, but that's because they're less clear anyway. If you are getting seriously stuck, there are solutions there as well in the folder, so you can sort of have a look at those, run them. But of course, I encourage you to have a go at trying the examples yourself to see what happens. And then there is as I said, a live input output here as well in a similar fashion. Talks you through all the various different things you can do on Spinnaker, and you can have a go at some tasks again at the end, a few different tasks. There is also a neurorobotics platform, which I think doesn't have the examples at the end. It just sort of takes you through running something on the NRP. If you want to have a go at that, you can. It's a little out of date, and I can see the picture at the top uses the old opening of a terminal in Jupyter Notebooks rather than Jupyter Lab. But I've shown you how to open a terminal. It's not too difficult anyway. If you've got this launcher, you just click on terminal. once you've got that, it's much the same. And you can try that out if you prefer as well. And basically, I am here, so I will listen in if anyone has any questions.